Well, my name is Lamija, and I present joint work with Leila and Senner. But first, I want to thank to you for the opportunity to speak up in this Fibonacci world. The first time as a speaker, but the second time as in organizing. Last time was online, and finally we are here in Sarajevo in class. In our work, we studied the zeta function and the Hurwitz-type zeta function associated to the Lucas sequence. We derived the asymptotic expansion of the zeta function in order to obtain the meromorphic continuation of the Hurwitz-type zeta function. And, well, I have.
Try clicking on the slide one more time. To take the mouse and just click anywhere.
Sorry. No. I can use this, no? Okay. I can use this, but
to go to the presentation.
Okay, now it's works. Okay. In the first part of this presentation, I'll talk about Lucas zeta function just a little bit and some properties we needed to derive asymptotic expansion of zeta function. So let's P and Q be the arbitrary real numbers as they satisfy these conditions. And then the Lucas sequence of the first kind for integer sum we can use this expression where A and B are roots of the quadratic equation given above. Zeta function in our theory carry important information about object they are related to, and zeta function corresponding to Lucas sequences of the first kind, we will call it Lucas zeta function, was described by Ken Kamanov, and he gives us in detail actually polar structure of the Lucas zeta function, and we'll use that in our work. It's easy to prove that the Lucas sequence and the corresponding Lucas zeta function possess these three properties. The first two properties can be easily derived from Ken Kamanov's work, and the third properties actually follow from the fact that limits of u sub n tends to infinity when n tends to infinity. Here we collect 4 cases when the Lucas zeta function possess both negative integers. We collect 4 cases depending on the value of the number q. The first 2, when q is equal to 1 and q is equal to -1, follow from Kamanov's work, and the third and the fourth was more. I need the word, sorry. We need to be more careful to derive the third and fourth, more careful to find relation between A and B when we have to get negative poles of the Lucas zeta function. For all 4 cases, we also derive the constant term of the Lorentz series expansion at negative integers, and it's given by this relation where h sub n denotes the harmonic number. Our first example, well, we took the special case when P is equal to 1 and Q is -2. For this case, yes, we of course have Jakobstahl numbers. It's obvious that the roots of corresponding quadratic equation are 2 and -1. Of course, logarithmical absolute value of -1 is 0. And now we may apply the fourth case of previous statement to imply that Jakobstahl zeta function possesses, which is actually initially defined for positive value of S, but we derive that it possesses meromorphic continuation to the whole complex plane with simple poles given by this first expression. And the special case is when it has, we can see that it has negative poles at even negative numbers. On the second part of this presentation, we focus on theta function associated to the local sequence of the first kind. We will give some properties and asymptotic expansion of the theta function. This function is defined for positive value of t by this, and it can be, we can use this expression. So theta function can be written as Mellin inversion, using Mellin inversion formula applied to the function zeta sub u times gamma classic gamma function of S. The reason for that was the zeta function is homomorphic and it's also convergent function. Okay. In this statement, we give asymptotic behavior of theta function for a small and huge value of t, and we also obtain that the sum, which corresponds to theta function, is absolutely convergent function for t in t0 infinity, where t0 is positive. It needs to have a positive effect. And our first theorem is giving us an asymptotic expansion of the theta function when t tends to 0. The values m, c, sub a, b, d, sub a, b, and are given in the next slide. It's not so beautiful. It's simple, but to prove this result, we use that theta function can be written as Mellin inversion, using Mellin inversion formula, and also we hire the residue theorem to calculate poles and corresponding residues to that function, and put it all together, and we get this asymptotic expansion of theta function. Okay, this is just. And on the third part of this presentation, I'll talk about the polar structure of the Hurwitz-type zeta function associated to the Lucas sequence of the first kind. But first, when we talk about the Hurwitz-type zeta function, it's defined as this sum, and it can be written as by using Laplace Mellin transformation applied to the theta function, and it will be actually our starting point in the proof of this theorem, which gives us meromorphic continuation of the Hurwitz-type zeta function, and we identified poles. That poles are at negative integers, -L, and okay, it works. And poles are also at this point. The corresponding residues are given by these two expressions. I also have that C sub AB are given. Couldn't fit in this one slide. Okay, and we our approach is different from approach given by Egami, Murti, and Navas, because they used Taylor series extension. We couldn't use that because we didn't have a Vinay-type formula for the series UN plus Z. So our starting point was actually to look at the function gamma of S times Hurwitz-type zeta function zeta sub U S Z and express that function as a Laplace Snelling transform of theta function. But we also couldn't use the approach given by in lecture notes by Jorgensen and Grant, because there we needed to have finitely many poles in every strip. But what's our problem? That we had infinitely many poles in every strip of weight more than one, and that to solve that problem, we need to calculate the theta function and the asymptotic expansion of the theta function. Well, this result can be generalized because we explain how to find the meromorphic continuation of the function corresponding to the sequence, which can be written as using the recurrence relation of order 2, and we suppose that it can be generalized by using recurrence sequences of order 3 or okay, I give you two more. Okay. On the first part of the presentation, I give two examples which correspond to two different sequences. The first sequence is this, when where elements UN are given as the first 10 elements of the divergent sum, and the corresponding Hurwitz-type zeta function is given by this relation. Using our results, we conducted that this Hurwitz-type zeta function possesses meromorphic continuation to the complex S plane, and we identify the poles of that function are given in this form. And corresponding residues are also calculated for those poles and this function. The second example is when we take the sequence of Fibonacci numbers, and for that sequence, corresponding Hurwitz-type zeta function looks like this. It possesses a meromorphic continuation to the complex S plane, and corresponding poles are given in these two ways, and the residues are. I run through this presentation. And thank you for your attention.
Can you go back to your slide for the sum of the Fibonacci addition?
This one?
Yes. And so if you take your z going to 0, what integers do you get next results from this? If we have generating functions for Fibonacci numbers times x to the n, does this reduce anything nice? S to sorry, S to are there any nice formulas for special values to see that you can get from this?
You're asking special values of z
Right.
or z.
Z or S? Z.
Z variable.
Or it would be both Z and S. You know, S so that things converge in a nice traces of Z. The sums of reciprocals of Fibonacci numbers or squares of.
But those results are already known.
Right, I'm just curious as to.
We didn't play with that, if you were asking, but may.
Because when you put z equals to 0,
Right.
what you get is well-known
Correct,
zeta
correct.
function associated to Fibonacci
Right.
sequence. So, I mean, you
Like
can
half-
put any
half
other
integer-
vector.
You're saying half integers and stuff like that. Is this reduced to something that's already known?
I don't know, maybe. I
I
mean,
know there's a lot of interesting differences in the behavior of the Riemann zeta function and things shifted by half. And I'm just wondering if you see any similar phenomena.
what was interesting to see is that you have all those poles in negative integers,
Right.
like for the usual Hurwitz zeta. And if you scroll back the next slide, I think this can be given an interpretation. I mean, we computed it. Just let me see what it is. My laptop does not want to open. So if you look at this right-hand side, actually we computed, I found it, I mean, it's written. So when you look at the square root of golden ratio over 5 plus the square root of golden ratio conjugated
Right.
over 5, and you add z to the L,
Mhm.
this is actually the constant term.
Okay.
That's I mean, for each of these examples, when you take a negative integer and compute the residue, then actually the residue can have some interpretation. And for me, it was curious that you get some type of like constant term in a certain expansion with just looking, because those usually when you take a look at Hurwitz zeta, I mean the residues that negative integers, they're related to Bernoulli polynomials. And so this is some type of generalized Bernoulli polynomial, and we were trying to see, okay, what type of generalized Bernoulli polynomial it is. But you somehow,
This would still be nice to see some happens.
I think so. I think so.
Yeah.
So we can try that. That's a great suggestion. We can plug in some special
Exactly.
values of z and c.
Right, and you already know what's going on in C.
What's
Zero
going
and
on.
C, what's you at.
Yeah. But we were trying actually to see what type of generalized Bernoulli polynomial this is.
Right.
Our,
Yeah.
our idea is to generalize.
Yes.
Right? Okay, and next idea is to generalize more.
Right.
But, okay.
My question is more quite because what I understand here is from the teaching formula and from the sample is that this technique works very well when you have the first initial condition equal to 0. But what about when the first initial condition is not equal to 0? So it's possible to adapt a whole technique to that case. I think it is very hard. Because that happens all the time. It's very hard. Maybe my intuition is telling me that you need something like a P evaluation or something. I think he knows more than I do.
I also did not quite understand.
No,
So
the idea
what
is,
are you
all
asking?
these techniques, you need to, your sequence, right, needs initial conditions, right?
Sure.
So, the beta formula says, okay, the initial condition says 0 and something, and works. But what about if you have initial condition not equal to 0, and the second initial condition not equal to 0? That is more complicated, of course. And my question is, have you tried to adapt this idea to that case that I'm telling you, two initial conditions not equal to 0?
Yeah, okay, I understand. So what the main idea here is that you can get an information about Hurwitz zeta function from knowing the theta function. And to know the theta function, you need to know the zeta function. So if your sequence has a unique type format, you can always get, irrespective of initial conditions, you can always get a neuromorphic continuation of the zeta function. And from the poles of zeta, you get asymptotic expansion of theta. And from asymptotic expansion of theta at t equals 0, there are techniques, analytic, to get neuromorphic continuation and poles of Hurwitz. So actually, this is like a 3 steps process, and you can do it for any sequence that has a unique type form and almost rebound.
But there are two cyclopedia formulas. One initial condition is 0, and the other one initial condition is equal to 0.
Yeah, but that's just when you take a look at the limit in the Binet formula. And in what you're asking, can we do it when the limit is not 0? And the answer is yes. Yes, because the technique works irrespective of the limit for the Binet sequence. Because we start with the Binet formula. If you have it available, irrespective of the limit, you can do it. Because, yeah, so.
Oh, yes, so I had a question concerning, usually when you look at a zeta function, the nice case is when you have a lower product. And this looks very much like you have no hope of having a lower product. And so I'm wondering what type of information you can extract from these zeta functions, like in terms of using the analytic information to extract information about sequences without the product formula in your hands, or if there is one, it's messy. Yeah, what kind of types of information have you tried to kind of go the opposite direction? So classically, in classical zeta function, the goal is not to say to measure the zeta function, but to use it to extract information about primes, just like this. Is there any analog of what information you can use these Hurwitz types of functions? What can you extract from the analytic information?
Let's see with the Z.
No, just like in general, like even for Z equals 0, like what types of, can you use the analysis by extending to the complex plane for S to like take contour integrals and extract information about the I've product formula, which would be very bad if it exists, and or from the sum formula.
No. Sorry.
Yeah,
Yeah.
okay, maybe I can respond. So this Hurwitz zeta is a bit tricky because it has a pole at S equals 0.
Yes.
So that for that reason it resists the contour integration, application of contour integration to get it. So for example, what you can do, there are different ways to regularize this zeta. So you can regularize it at 0 and then extract information. Like you can define, of course it does not exist, but if there were like an operator with eigenvalues to be Fibonacci sequence, then you can define the infinite product of Fibonacci numbers.
Yeah.
But using regularization of this data at S equals 0. Those are, I mean, analytic, very analytic techniques that are not really standard. There is a different type of data regularization when the function is not holomorphic in 0. But it still gives a meaning to an infinite product. So that's, for example, something you can do.
All right, thank you, our speaker.